example, under lecture 2, if we have this expression, we have b bar c bar or e bar b or e b bar c. So we have to redraw this using all none. So if we have to use all none, first, we have to let this first term as our x, or with your second term, and we have to let this one as your lowercase y, and then it is or with your third term, we let this one as your w. So if we have to write that in terms of your x, we have x, it is or with y, and or with w. If we are going to use a NAND gate, so we have x, we have your y, and we have your w as an input of your NAND. Now, using your De Morgan's theorem, we have to break this bar. So it will become x bar or y bar and your w bar. So as you can see, the original expression in terms of x, y, and w is just x or y or w without a bar. So if we have to use a none, there is a bar. So we have to eliminate that bar. So but just by adding a bar in each variable in your y using none. So this will become double bar for y, double bar, and for your w, it is also double bar. So it is now, the result will now become the same as your original expression. But what is x? Your x is equals to b bar c bar. But if we have to use a none for your x, so using a none, that is, we have b bar, then c bar, and a bar. So there is a bar that will connect your b and your c. So we have to eliminate that bar. So we have to add another bar. For your y, in your y, we have an expression of e bar and b. So if we have to use a NAND gate, so there is a bar in your A as an original expression. Then B, since it is a NAND, there is a long bar. So we have to eliminate this bar. So just by adding an inverter at the output of your Y. And for your W, we have an A, we have your B bar, and C. So if you have to use an AND gate, a NAND gate, that is A, B bar, then C. So we have a none. To eliminate that bar, we have to introduce another inverter at your output. So if we have now going to rewrite that expression in terms of what we have. So first, your x is equals to b bar, c bar, then it has two long bar. So this is your x. And in your expression for your output, we have another bar. So we have another bar, this one. So this, you have to add another bar. Then, or you have to put your y. Your y is e bar. Then b. We have 1 and 2 under your y. But in your output expression, there is still a bar. So we have to add. Then third input, we have a, b, bar, c. Then we have another 2 long bar, this one. And at your expression for your output y, there is another bar and your long bar. So in each term, we have 1, 2, 3 with the same length of your bar as well as the second term and the third term. So we can eliminate these two. This one, we can eliminate this. And also we can eliminate that one. So if we have to rewrite that again, so we have b bar, then c bar with long bar. So we have only one bar remaining at your first term. Second term, we have e bar, then b with one long bar. Third term, we have a, we have b bar, then c with a long bar, and your output none. So this is your expression if we are going to use all none. So first we have to draw your input b with inverter. So that is using NAND gate. We have input C also with inverter. So using NAND gate, so this is now your B bar, C bar, and it is connected with another NAND. So we have this NAND. So this is our X. Remember that is our X. Then for your next one, you have your A. So input A, it is complemented. So we have to do NAND gate. So this is a NAND gate for the inverter for your A. So you have A inverted and you have your B. So it is connected to your another and gate. So we have this B. So this is our B. So this is now your Y. And the third one, we have your B bar. So we have to do your 3 input NAND gate. First, we have your A, then you have your B bar, and we have your C. So this is your W. And after that, they are connected with a NAND gate as your output. So this is your Y. So you have this as your third input, this one as your second input, and this one as your first input. So this is now your circuit using all NAND.